This is Free Range Digital Design Foundation Modeling. This is Chapter 17. In this chapter, we'll introduce a new Digital Design Foundation module, a very useful module, which is the multiplexer, otherwise known as a MUX. So this is pronounced MUX, not MOOCs. Hardware has to make decisions as well as software. Now, you're probably familiar in software. You have to make a decision of essentially which code to execute. In hardware, it's a little bit different. Notice in software, what you're deciding is to execute one set of instructions or the other set of instructions based on some condition in the program. So the idea is, generally speaking, you have one processor, so you have one thread of execution. It's inherently, we'll say, serial. It just does one thing. It can only execute one set of instructions. Hardware is a little bit different because hardware is inherently parallel. It can do a whole bunch of things at the same time. I mean, imagine a circuit with different pieces of hardware all doing whatever it needs to do all at the same time. Hardware, generally speaking, you are not going to calculate one thing that you choose. You're actually going to calculate a whole bunch of different things. Choose the one you want. You're going to calculate a whole bunch of things at the same time. You're going to select which one you actually want to use in your circuit. So that will become more apparent later. So it is similar to software, but it's not exactly the same thing as software, based on the notion that hardware is inherently parallel, while most single processor systems are inherently not parallel. Multiplexer is a relatively simple device, particularly at its most simple forms. And what we have here on the right is a very simple form of a multiplexer, which is a 4-to-1 multiplexer. On the left, we have a familiar circuit, which is a standard 2-to-4 decoder. So the way the decoder works, we talked about this before, the way these select inputs are set up, it allows only one of these gates to be on at any given time, and the result is this outputs a one-hot code. Puts out one of 4 different numbers, and essentially what that means is one of these AND gates is turned on, the other 3 are turned off, depending on the select inputs. This is a 4-to-1 MUX. It's essentially the same circuit. You can see the decoder in there, but what we've done is we've added data inputs. So these right here are the data inputs. We have one data input per AND gate. So still the same principles apply in that based on these selection inputs, only one of these AND gates can possibly be a 1 at any given time, but the other 3 are 0. 3 of these AND gates are always going to be off. The way we've wired it up is one of these AND gates will be on, or it might be off as well. Now the difference is it depends on the data. So what happens here, for example, if the select inputs are 0 and 0, it will turn this AND gate on, because S1's 0 gets inverted, S0's 0 gets inverted, so essentially the top 2 inputs to this AND gate are both 1. So if the AND gate has one more input, it has a data input, which is D0. So if D0 is a 0, the output of this gate's a 0. If D1's a 1, the output of this gate is a 1. So essentially, the output of this gate is going to be D0. This is the OR gate. 3 of these inputs are guaranteed to be 0. This input here may be 0 and may be 1. So if it's a 0, essentially what happens is it turns this OR gate off, and we get a 0 on the output. If D0 is a 1, it turns this AND gate on, and we have a 1 on the output. So effectively, D0 appears on the output of this device. So when S1 and S0 are both 0, turns this gate on, it allows D0 to appear on the output of this device. So essentially what it does is it selects, we like using that term, it selects D0, one of the data inputs, to appear on the output of the multiplexer. According to these select inputs, we can always select one of these 4 data inputs to appear on the output. The other 3 are simply ignored. I don't know if that's the right word, but it doesn't become part of the problem. So once again, a very simple multiplexer here. We don't really use too many multiplexers that are that simple, but the idea is still the same. And it has a decoder, a standard decoder at the heart of this, and that's really what makes this device work. Here is an example, timing diagram example. work through this example here, and here what we have is here's the data inputs, here's the select input, and there's the single bit output. So these problems are always kind of can get messy, and so I try to make them as neat as possible. And so what I'm doing is drawing vertical lines associated with the select variables. So these vertical lines are indicators to me where the select variable is changing. So this first select variable is 0, 1. That means it's gonna select this data input to appear in the output, and that is a 1. This 1 here represents that 1 there. Okay, here's what happens here is the select inputs change, and so it's going to do a different selection. It's selecting 3. Here's 3. 3 is also 1, so once again this is that. Here I go back to 1. 1 is also high, so let's select 1 there, and then I go to 0. Okay, so 0 is a little bit more interesting. It's selecting this line. This 0 here is selecting this D0 line to appear in the output, so it's going to go low, and then somewhere in the middle of that interval it's going to go high. And so what we see here is this signal here matches this signal there. For 2 it stays high. This is that. Here we have a 1. It's selecting the 1 input to be on the the 1 input, which is this one, to be on the output. So I'm going to take this, drop it down here. Here's the 2. The 2 is this line right here, and lastly we have the 3. The 3 is going to take this line and put it on the output. Okay, so there's our output signal, and that's all we get. So once again, these select inputs are selecting which of these 4 bits to appear on the single bit output. Examples we did, and the circuit we described as being a multiplexer is extremely simple. It works well with buses also. And so the issue here is you certainly wouldn't want to design this the way we designed it before, because it actually has 34 inputs. Okay, so that's going to be a very large table. You're just not going to want to design that circuit. But it's still the same selection criteria, and what I'm going to do here is mark when these select variables are changing. So I'm going to mark that with vertical lines so I know what's happening here. So I still have 4 inputs. With 4 inputs I have 2 select variables. It's going to select which of these 4 inputs is going to appear on the output. Now necessarily the width of the data inputs match the width of the data output. In this case these are all 8-bit. Let's look at this thing here. This first select variable is a 2, and I come over here and look at 2 and check it out. Here's my 2. This 2 match is essentially an indicator that this is what's being chosen here. So AY appears on the output. Here's AY, and that is 0x22. So here's AY22, and there it is there. So we got the select variables changing to 0. 0 is associated with AW, so it's these 2 signals right here that appear right here, which is going to get kind of messy, but got to do it. So this value here is 0x24. This value here is 0xCF. So once again, this, because of the 0, is selecting AW. AW appears on the output. Okay, next we have 1. 1 is AX. So this is going to be another messy one. Okay, so here's AX. This is transferred to the output. So that's a 0x80. And here's a 0x03. Okay, so we're back to 0. 0 chooses AW. I can see a data change right in the middle of that, and we have CF. Remember, this CF here is this CF, and then we have 1A right there. Looking good. Almost done with this problem. Lastly, we have 3. 3 is AZ. AZ happens to be 0xEF right there. So this 3 chooses this AZ output which is this, AZ input to appear in the output. You haven't seen this before, but this is the distinctive mux shape. We always use that for a mux. When you see that in a circuit diagram, you know the circuit's making some type of selection. Data widths of the inputs match the data width of the output, and that's it for this thing. So this is an example of a circuit where I'm going to have to make a selection on it. Now I can see that because I see this circuit has a button. It tells me it's choosing an A plus C or an A plus B depending on which operation is selected by the button. Now this means this circuit cries out for data selection. When I see data selection in hardware, it always means a mux. There's no other way to do it. When there's a choice to be made in the circuit, you use a mux. What we need to do is first draw the top level black box diagram. I think we'll draw it 3 unsigned, A bit, 3 unsigned values, A, B, and C. These are all 8 bits. It has a button input called out by the problem, and it has an 8-bit output. So there's the top level, and what we need to do in this circuit is figure out how to make the circuit work here. And so there's an interesting constraint here, and that's only use one ripple carry adder in your design. Now the issue is you could do this circuit different ways, but constraining it to use only one ripple carry adder kind of makes the circuit such that you can only do it one way. There's a decision being made in this circuit, and that's to either add A plus B or A plus C. So I only know how to add one thing with a ripple carry adder. Other nice thing about this problem is it doesn't, I don't have to worry about any overflow or carry out or whether the answer is valid or not. It told me to assume it's always valid, so that's good. The operations this is doing is A plus B and A plus C, so that if you look at this, A is always being added. So we'll put A in there because we know it's always being added. But what's happening here is sometimes I'm adding B and sometimes I'm adding C, which means I'm making a choice. I'm making a choice whether to add A or B. Anytime I make a choice like that, it's going to be a mux. And there's my mux. The mux always has a control input, which decides what value is going to be passed along. That's necessarily connected to the button, and we'll throw this sum in here also. And so we're almost done with this thing. It looks like it's done, but we absolutely need to put numbers inside this mux here to make it kind of disambiguate what's being chosen there. So it says it does A plus B if button is a 1, so there's my B and there's my 0. So if that button is a 1, it selects B to appear on this output, and it's going to add A plus B, and that's going to appear in the output of the circuit. Now if button's a 0, that passes the C through this mux, and it's going to be the A plus C value, and that is the entire circuit. The other way you could do this with 2 ripple carry adders, I'll do this really fast, is to add A to both circuits and then add B to one circuit, C to the other circuit, and put the mux on the outside. Okay, so the idea behind this circuit is it uses 2 ripple carry adders and then a mux, and here's your button. And this one uses 1 ripple carry adder and a mux. So this one necessarily here is a better circuit. By all means, this is one you should strive to use in your circuit design. Lastly is the multiplexer foundation module. Here it is as a mux. This happens to be a 4-to-1 multiplexer. There's 4-to-1 inputs there, and because there's 4, I need to select between 4 things, so there's necessarily a 2-bit select variable. So once again, the select variables select which of these data inputs that's going to appear on the output. Ends always match, and what else is interesting about this circuit? It does have the distinctive shape that you will always use for a mux, because when you use that shape, it transfers information. And lastly here, general flavors of the mux are 2-to-1, 4-to-1, 8 to 1. You could essentially have anything in between, but it usually has a binary type relationship to the number of data inputs, and the output's always 1.